Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. I welcome you all in class of real analysis by Robert G. Bartle. Today lecture is a very important topic. Actually, in this lecture, I will discuss the core topics of real analysis. We are going to start section 2.3. In today's lecture, we will discuss lower and upper bound of a set, bounded above and bounded below sets, bounded sets, supremum and infimum of a set, and lastly the completeness property of R. So I hope you will enjoy from today's lecture. So let us start from the definition. Lower and upper bound of a set. Let firstly remember, lower and upper bound of a set is always a number. This is not a function, not a set. These are always a number. Lower and upper bound are always a number. How can we define it? Sorry, just a minute. Let S be a non-empty subset of real number. A real number capital M, which is greater than or equal to all numbers of set S, is called an upper bound of S. Symbolically, an element capital M belong to R is called an upper bound of S if M is greater than or equal to S for all S belong to capital S. Similarly, an element small m belong to R is called lower bound of S if this real number is less than or equal to every element of set S. For example, if I have a set S is equal to 1, 2, 3, this is the these are the first 20 natural numbers, be a finite set. Since every number of S is less than or equal to 20, so 20 is an upper bound of S. On the other hand, as element of S is greater than or equal to 1, so 1 is the lower bound of S. Bounded above and bounded below sets. If set S has an upper bound, then S is called bounded above. If set S has a lower bound, then S is called bounded below. Lower bound mean bounded below. Upper bound mean set is bounded above. Bounded set. A subset of R which is bounded above as well as bounded below is called bounded set. Since for the set in example number 1, 20 is an upper bound. In example number 1, our set S is set consists on first 20 natural numbers. So in this set, you can see that 20 is an upper bound and 1 is the lower bound. So the set S has an upper bound as well as lower bound. Hence, the set S is a bounded set. Supremum and infimum of a set. Let S be a non-empty subset of R, then the smallest or the least upper bound of S is called supremum of S, and it is denoted by sup of S. Similarly, the greatest or largest lower bound of S is called infimum of S, and it is denoted by inf of S. As in example number 1, 20 is an upper bound of S. Also 21 is also an upper bound of S. Similarly, 22 is also upper bound of S. So all the real numbers which are greater than or equal to 20 are all upper bound of S. So actually for set S is equal to 1, 2, 3 up to some 20, all the real numbers which are greater than or equal to 20, and if you plot these real number on the real line and say this is x is equal to 20, then all the real numbers from here to positive infinity represent the upper bounds. These are the upper bounds of set S. But the smallest upper bound is 20. So this is called the supremum. So supremum of S here is 20. Similarly, all the numbers which are this is the smallest number of this set, that is 1. Now all the numbers on the left of 1 to positive negative infinity, all of these numbers are called the lower bound of S. Lower bound of S, like 0, -1, -1.5, -1.2, minus pi, etc. are all the infimum of this set. But among all of these lower bound, the greatest lower bound is 1. -1.5, 0, minus pi, -2, these numbers are, all these numbers are lower bound. But among all these lower bound, the greatest or largest lower bound is 1. So 1 is the infimum of set S. Next, it is not necessary that the supremum and the infimum of a set belong to that given set. For example, in our example number 1, both supremum and infimum of this set S, this is the supremum and this is the infimum. Both are the part of set S, but it is not necessary that supremum and infimum always belong to the given set. For example, consider this set whose elements are 1, 1 by 2, 1 by 3, up to so on. And these numbers are also continue here. You can observe that the numbers 1 by 2, 1 by 3, 1 by 4, 1 by 5, up to so on, this number goes to 0 as an approaches to infinity. Whenever you increase the denominator, this fraction becomes smallest and it approaches to 0. So 0 is the infimum of this set S. But you can observe that 0 is not an element of this set. You cannot approach to 0. Although this number approaches to 0, but you cannot exactly find a fraction which is equal to 0 here. So 0 does not belong to this set, although the infimum of this set exists but does not belong to set S. So this example shows that infimum does not belong to the given set. Similarly, consider this another set J which having the elements 0, 1 by 2, 2 by 3, 3 by 4, 4 by 5, up to so on. If you consider these numbers 1 by 2, 2 by 3, 3 by 4, 4 by 5, these all number approaches to 1 whenever your n approaches to infinity. Actually, the general term of these numbers is n over n plus 1. This is the general form of these numbers. So whenever you take limit n approaches to infinity, this is equal to 1 here. So these numbers approaches to 1. The first number 1 by 2, this is 0.5. The second number 2 by 3, this is 0.67. Third number 3 by 4, this is 0.75. 4 by 5, this is 0.80. So you can notice that whenever you increase the numerator as well as the denominator, your numbers approaches to 1 here. So 1 is the supremum of J, but you can notice that 1 is not an element of J. So 1 does not belong to J. So this example shows supremum of set does not belong to given set. Next, completeness property of R. This property consists on two properties. The supremum property. What is the supremum property? Every non-empty subset of real number which has an upper bound has a supremum in R. For example, in above example, you can notice that when your S is a set of first 20 natural numbers, clearly S is a subset of real number, Now S has an upper bound, Clearly 20 is an upper bound of S. 20 is equal to upper bound of S. This property says, supremum property says, this set S must has a supremum in R. Must have, and you can notice that 20 is also supremum of this set. Similarly, in this example, you can notice that although 1 does not belong to this set J, but 1 is an upper bound of this set, and this set clearly is subset of real number. Now, if J is subset of real number and J is bounded above, because 1 is an upper bound, Upper bound means an element which is greater than or equal to every element of J. So clearly 1 is greater than every element of J, so 1 is upper bound of J. Now supremum property says if there exists an upper bound of J, then it must have the supremums. You can notice that there exist many upper bound of J, like 1.1, 1.01, every real number which is greater than or equal to 1 is an upper bound of J. So among these upper bounds, the smallest upper bound is 1. So the supremum of J must exist, that is 1 also. Similarly, the infimum property can be defined as if every non-empty subset of real number which has a lower bound has the infimum in R. Now, if your set has a lower bound, then it is guarantee that the set has infimum in R. For example, again, in this example, your lower bound of set S is 1. 1 is the lower bound of S. And the set is subset of real number. So infimum property guarantees that the infimum of this set must exist. And you know the infimum of S is 1. Both property can be summarized as every non-empty bounded subset of real number has supremum and infimum in R. So in some context, in some textbook, you will see author just consider the supremum property as the completeness property of R. Because we will verify that actually the supremum of A is equal to minus time infimum of minus A. Similarly, infimum of A is equal to minus time supremum of minus A. We will verify this result. So that's why if the supremum property hold in set of real number R, then automatically infimum property also hold. That's why there is no need to separately verifying that the supremum and the infimum property hold or not. If one of the property hold, then we will say that this set has completeness property of R. So I hope now you have a clear understanding about these concepts. If you find any difficulty, any question, you can message me. Inshallah, I will reply you. So see you in the next lecture with a new topic. Take care. Allah Hafiz.